So there are 3 cycles we're going to cover. I think I'll split into 3, just 3 parts. One for the Rankine, one for the Brayton, and one for the Otto cycle. So the way the cycles work is it's essentially a series of components attached together. The components are what we covered in the past 2 weeks. So pumps, turbines, compressors, etc. All of those things are now, we're going to put them into use. We'll put them together for a useful purpose. You'll see me mentioned, I tried to make these notes as complete as possible. You have the name of the cycle, its use, the diagram, like the component diagram, the processes involved. And you'll see I'll mention a number of times isentropic, and this is a TS diagram, S being the quantity for entropy. I included that vocabulary even if we haven't covered it yet, because we will, and then you can come back to it and it'll make a little bit more sense. We don't need the notion of entropy for now to solve everything correctly, but I included it in these notes here for future reference. So you can come back to the isentropic process and see what that means. But for now, you can ignore the word isentropic. We can still solve the question fairly easily regardless. So a Rankine cycle is what I have here. And it's a power generation cycle. And it's using, this one is water, important, meaning tables, okay? So the way it works is I have steam and water. So we'll be talking about mixtures. So I'm going to start down here. And at this stage here, stage 1, I'm a liquid because pumps only accept liquids. That's an important thing to remember. So I'm over here, I exist happily at this stage. And then I go through the pump. The pump is used to increase pressure. And it's doing work on the liquid, okay? And it accepts liquids only, no gas. It would be sad if you try to put gas in there. So we're increasing the pressure until we hit this point, point 2. At point 2, we go through the boiler. As the word suggests, boiler is a Q in, okay? So we're adding heat to the system, and the boiler works at a constant pressure, which means that P2, so therefore P2 is equal to P3. That's another important fact. So we're boiling it basically until we hit gas. We need to hit the gas state, and then we're going to send it through the turbine. What the turbine does is it's going to extract work. We're going to get a work out, which from our sign convention we know should be positive. And this is the useful portion of the turbine here. It's the useful portion of the cycle. The turbine is what we want. We want to maximize the amount of work coming out of the system. All right, because as I said, it's a power generation cycle. We're boiling water in order to hopefully get electricity out of it. All right, so after I've got as much work as I can out of the turbine, I go into the condenser, which acts as a Q out. It needs to cool until we get back to a liquid. All right, that's what this cycle is doing. A couple of important things. Turbines, I say it's gas going in. It almost always will be. But coming out, we may be removing enough energy that it might drop to a mixture. So we have mostly gas with a little bit of water droplets. So we're not necessarily a gas coming out of the turbine. Most of the questions will specify a quality. So that's a little set of notes here. And then next we're going to solve a Rankine question. So the question states that steam is the working fluid in an ideal Rankine cycle. Saturated water vapor enters the turbine at 8 MPa. So at this stage, we know we're at sat vapor. The flow leaves the turbine as a saturated two-phase mixture with a vapor quality of 67.45%. So we know there's a value of X here. So we're a mixture down here. Saturated liquid exits the condenser. So here we know we're sat liquid. And then the pressure there is given. The net power output of the cycle is 100 megawatts. The pump consumes a specific work of 8.06 kilojoules per kilogram. Calculate, there's a couple of things they want. They want thermal efficiency of the cycle, mass flow rate, the rate of heat transfer in the boiler, and the condenser, megawatts. Calculate also the mass flow rate of the condensing cooling water in kilograms per hour if cooling water enters the condenser. So what they're saying is essentially, so we know the condenser is a Q out. So instead of just throwing that heat into the atmosphere, they're asking us, what if we put a flow of water. So this is hot to cold, like this. And then we're going to take the Q like this. So we'll take the Q of the, we'll take the Q from the, our cycle water, and then we'll extract that heat using a second loop, essentially. Okay, I'll have a better diagram of that when we come to it, but that's essentially what that last part of the question is asking. All right, so given what they told us about the states, saturated vapor, saturated liquid, and mixture, I can get a lot of information out of the table, and these questions are actually, once you sort of figure out all of the phases, everything that's being asked, are not all that complicated because we've covered all of these components already. Okay, so my knowns here, I know that the total work net is 100 megawatts, and I know that the work of the pump is 8.06 kilojoules per kilogram. Now I'm going to look at the phases at each state. The phase, I mean the phase of matter. So at 1, I know that I am a saturated liquid, right? So that way I know that VF is going to be equal, for VF, V1 is going to be equal to VF, which is, here we go, 0.001008 meters cubed per kilogram. So I have my V1, and I can find my H1, which is going to be equal to HF, right? Because we're a saturated liquid. And the pressure is known, right? Because the pressure here was given. So we know that here we have exits the condenser at a pressure of this. So we know that this is P4. Well, it says, okay, exiting the condenser. So we know that's state 1 when we exit, when we exit the condenser. So that's P1 equal to P4. I also have the pressure here. When we enter the turbine at 8 MPa, so this is I'm exiting the turbine at 8 MPa, so this is giving me P3. But knowing that the boiler is at a constant pressure, we know that because boiler at constant pressure, we know that P2 is going to be equal to P3. We can work that pressure backwards. So I'm just going to rephrase this so that it's a little bit clear where I'm getting my numbers. So at 1, we know that pressure was equal to 7.5 MPa. Sorry, 7.5 kPa. Or I'll just use the numbers they gave me there. So at state 1, we know that pressure 1 is 0.0075. So we'll check, yeah. And then I can, knowing the that it's a saturated liquid, I can get those numbers. I didn't write HF down, was 168.79. Now I'm going to go look at state 4. At 4, I know that P4 is equal to P1. And at that state, I have a quality, right? So I know that H4 is going to be equal to HF plus XHFG. HF I got out of the table. They're actually right there. My HF is actually right there, but it's 168.79 plus my quality was known. And my HFG from the table, 2,406, gives me a value of 1,791.64 kilojoules per kilogram. Right now I'm just getting all of my knowns from the table. And then we know at this is a sat liquid. And then we know that P4 is of an X, is 64. Just to try to indicate here where I'm getting my numbers. There we go. And I believe there's one more point where we know, where we have all of this information. It's going to be at 3. At 3, we know the pressure up top. After we've gone through the pump, we know that pressure is going to be 8 MPa. We know that P3 is 8 MPa. We also know, coming out of the pump, we're still liquid, right? We can only deal with liquids. All we did was increase the pressure of the liquid. So we know that we're still a sat liquid. And this will give me a H3 equal to H. Hold up. Sorry, no. My bad. Stage 3. Stage 3 is up here. It's after the boiler. Sorry, after the boiler. And then we're at a sat vapor. And because the phase, we know the phase at that stage because it was given in the question here. Saturated vapor enters the turbine. So at stage 3, we have a sat vapor. So we know that H3 is equal to Hg at that pressure, which gives me a value of 2,758.0 kilojoules per kilogram. Now these are all of my knowns. This is all the information I can get directly out of the table, all right? So now we're gonna start looking at each one of the components one by one. Because I don't know the mass flow rate, at this stage it is very difficult to find total work. However, we're saved a little bit by the fact that the question asks the mass flow rate, so anyway, given that we don't know exactly the flow rate, it's going to be a little bit hard to find our total work. So instead, I'm going to look for the specific work. I'm going to start by looking through the condenser. If you look at the condenser, there's a flow in and a flow out for now. That's all we need to take care of. It's a flow in of water and a flow out of water. What we know about a condenser is that there's no work, right? All we're doing is it's a Q out. So if I look at my equation for the first law, it's steady state. So there's no dE over dt. We know there's a Q. That's the important part of the condenser. There's going to be no work. It's what the device does. It does not do any work. There's going to be a mass flow rate in and a mass flow rate out, and we're going to be neglecting all of the changes in speed, changes of height, because as we checked this in the previous problem set, the changes in speed, the delta KE is very, 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 very small compared to the amount of work we're doing. So having looked at it this way, we said that it was steady state, so dE over dt is equal to 0. Q is important. There's no work done. And then I know that my flow in is the same as my flow out. So my sum of flows, if you need a little reminder, so it's the sum of flow in H in minus the sum of flows exit H exit. That's all I'm considering. And we know that the flow rates are the same. So I'm going to get H, this is H4 minus H1. However, considering that I don't know my mass flow rate, which is a little bit annoying, I'm going to solve for lowercase q instead, which instead of being in watts, will be in watts per kilogram, which is which is going to be H1 minus H4. Just watch the signs. What I ended up doing is I just brought my m to the other side of the equation, which flips the sign here. And if I do this subtraction, my H1 is up here, my H1 is up here, my H4 is over here. So H1 minus H4 gives me a value of 162.847 kilojoules per kilogram. Next, I'm going to look at the turbine. My turbine is the opposite of my condenser. If I look at the turbine, I'm getting work out of it, right? There's going to be work done on the fluid, but there's no heat exchange in a turbine. So if I look at my first law equation, steady state, so there's no dE over dt, there's no heat exchange, there's work and there's a flow. Okay, so this equation is often going to be reduced to, for the cycles, heat, work, and flow, more or less, okay? So steady state, no work, no heat, there is a work. And my turbine is H3 over H minus H4, which means that, ooh, whoopsies. Hang on. Steady state equal to 0 minus work plus m dot H3 minus H4. I'm building these equations by looking at them one component at a time. So if I look at my turbine, 3 is my in, 4 is my out. Okay, so 3 in, my sum of flows in, minus my sum of flows out in 4. So I'm going to again rewrite this in terms of specific work because I don't know my flow. So I'm going to say that lowercase w is going to be equal to H3 minus H4, just dividing both sides by mass. And those numbers I have both up here, H3 right here, H4 is right there. I'm going to save the arithmetic. This is mostly to show how these questions are processed because they can be kind of lengthy. So that gives me a value of 966.36 kilojoules per kilogram. So there's my work of the turbine. Now I have to look at my work of the pump. Why am I going to look at the work of the pump? Because I know the value of the work of the pump. Well, I know the value of the work of the pump, but what I'm really interested in order to answer the question here, is the steam. Is the heat transfer into the boiler. Okay, that's part of the question, is part of what I'm trying to solve for, but I don't know H2. I don't know anything about that point in the diagram. Okay, I know the states of all of the other points, so I was able to find the values from the table, but I know nothing about that state. However, knowing the work of the pump, I can reverse engineer the enthalpy at that state. So if I go next to the pump, and if we look at what pumps do work. They're adiabatic, so there's no heat exchange. Okay. So we know that 0 is going to be equal to no heat exchange. Work, it does work. My mass flow of my in minus out. Now I'm just going to rewrite this in terms of specific work, again, because that's actually what's given in the question, is a work in kilojoules per kilogram. So my work is going to be equal to H1 minus H2. My work was minus 8.06 kilojoules per kilogram. My H1 was known, 186.79 minus H2. If I rearrange, you'll see that H2 is 176.85 kilojoules per kilogram. Now I can go look at my boiler because I know the value of my enthalpy at state 2. So my boiler is treated very much like the condenser. It just does the work, the heat flows just in the opposite direction. So we know in steady state, there's going to be a heat exchange. That's the important part of the boiler. Boilers do no work. And then I'm going to have a flow. H2 is my flow in. H3 is my flow out. So knowing that, again, I can only solve for specific for right now. So I know that Q is going to be H3 minus H2. Again, I flip the signs because I'm rearranging my equation here, bringing Q to the other side, and then I'm flipping the signs. And this gives me a value. You can copy H2's up there, H3's up there, and that will, the subtraction will give me 2,581.15 kilojoules per kilogram. My work net, the work net in this question was given at 100 megawatts, right? So my work net, which is the total work I'm doing. So this is, okay, I should be more careful. This is a lowercase for now. My lowercase work net is going to be the work of the turbine plus the work of the pump. Okay? It's the sum of all of the works I'm doing. So the turbine had a positive, so let me label things here. So my turbine here, my work of my turbine is here. Work of my pump was given in the question. Right, we were told it was minus 8.06 kilojoules per kilogram. So the work of the turbine, I calculated above, 966.36 kilojoules per kilogram, plus, note my signs here are important. I'm saying it's the sum of them, right? And the work of the pump is a minus like this. Okay, I'm assigning the, I'm always saying that I'm always summing my works, okay? Assuming that everything is a sum and that the work outs are going to be negative, okay? And then I'm not just, the alternative, you could always write your equation in this way, that the work of the turbine is you can look at it like this, is minus the absolute value of the work of the pump. Because we know that the work of the pump is coming out of the system. Okay, so that's one way to look at the equation. I choose to instead say that it's the sum of my works, because it's a net, right? A net is going to be the sum of work 1, work 2, work 3, work 4, work 5. And the sign of my work is built into the number as if my number was a vector. Okay, so that negative sign is part of my work P. My work P is a negative 8.06 kilojoules per kilogram. Okay, I'm building that negative sign into the number as if it was a vector. I hope that made sense. If not, you can always ask me questions during the tutorial, but there are several different ways to manage your positive and negative signs. This is how I do it. I find it a little bit easier. So this sum will give me a value, I'll write it over here, of 958.3 kilojoules per kilogram. Next, I'm going to look for my flow rate. I know that actually, ooh, these are not dots. These ones are not dots. Okay, there we go. So I know that my mass flow rate is going to be equal to my work minus my specific work. And if you look at the units, it'll make sense. So my total work net was, 10 megawatts. What was it given as? 100 megawatts. Oopsie. 100 megawatts is, I'm going to go times 10 to the 3, which will give me in kilowatts. And remember that the unit of a watt, I'll just write it in brackets, or no, I'll put a slash. Brackets look like a multiplication. So remember that a kilowatt is a kilojoule per second. And then my work net, I just calculated at 958.3 kilojoules per kilogram. If I look at how the units are going to work out, I'm going to, kilojoules and kilojoules will cancel, and I will be left with per seconds per kilogram, which comes back up top and will give me kilograms per second. And this gives me a value of 104.35 kilograms per second. I think the question specifies kilograms per hour, so what I'm going to do instead is 104.35 kilograms per second times the fact that 1 second times the fact that there are 3,600 seconds in 1 hour. And this will give me a value of 375,665 kilograms per hour. Let's just check that we answered everything. We have heat transfer, rate of heat transfer. We got the mass flow rate. Oh, actually, we didn't fully answer that question. All right, let's just go through everything we have here. Calculate, we didn't do efficiency either. So mass flow rate of steam in kilograms per hour is check. And here they're asking for the rate of heat transfer in the boiler and the condenser. Did we calculate that? Not quite. What we have here is a specific heat, right, in kilojoules per kilogram. So the rate of transfer would be, to make sure that we actually answer the question, rate of transfer in kilowatts is going to be Q dot, is going to be Q times M dot. The dot is a notation in per second, all right? So let's do this to make sure we've answered the questions properly. So the condenser here was 1622.84 kilojoules per kilogram. I'm going to use our value in per second because it was 104.35 kilograms per second. So again, if you check my units, I'll get kilojoules per second, which is a value of watts, kilowatts in kilojoules per second. I didn't actually compute this, so I'll do that quickly. All right, this will give us 169,343 kilowatts, because a kilojoules per second is a kilowatt. We'll have to do the same thing for our boiler. So condenser is a Q. Well, condenser should be the Q out. So H1 minus H4. H1 is much less than H4. So this should have been a negative number here. If you do the arithmetic, H1 is smaller than H4, correct. Okay, because it's a Q moving out, obviously. So there's a mistake here. There we go, that makes more sense. Q out. That's what I meant where I leave the sign built in. So I'm gonna need, so this is a Q out. This is my Q in, is going to be equal to my Q, my specific work times my mass flow rate. So 2,581.15 kilojoules per kilogram times 104.35 kilograms per second, which will give me a value in kilowatts. And that value will be 269,343 kilowatts. All right, so we've properly answered the question now. So we did get a rate, because a rate means it has to be a per second value, okay? And a kilojoule per second is a kilowatt. So we did properly answer those now. And the last part that we're asked to answer is the thermal efficiency and cooling water entering the condenser. I'll talk about that in a second. So we'll start with the efficiency. Oh no, I need some more room. Oh, I thought I had given myself, OneNote is such a pain doing this, and I thought I had given myself enough room. Okay. All right, there we go. So now the efficiency. What is efficiency, you ask? I have not yet mentioned it. So this is my efficiency, and my efficiency is going to be my work net over my Q in. Essentially what that means is my work net is my useful work. Divided by my Q in, which is my cost. Because my work net is the sine of, the sum of my turbine and my pump, what it's essentially telling me is my turbine gave me 966 kilojoules per kilogram of work, which was good. It was useful. That's what I wanted. But it costed me 8.06 kilojoules per kilogram, which is not useful, which was a loss. So by doing the sum, I'm giving my net, and that's everything that was useful. I took away what was useless. I took away my cost from my net. And then the same thing with my Q in. It's going to be what it cost me. Okay? So that's how this expression is derived. So it's useful over cost. And because of this, because of the laws of thermodynamics, you would expect a value of less than 100%, right? Because if not, I'm spontaneously creating energy. And we know, unfortunately, the universe doesn't allow for that. So my work net, I calculated up top, was 958.3 kilojoules per kilogram. And at my Q in, I took it up here, 162. My Q in is from the boiler. Here we go. 258.15 kilojoules per kilogram. And it gives me a value of 37.1%, which is pretty good for these kinds of cycles. You'll see here, these are my capital rates. It is the same thing if I do work net divided by Q in, as long as the units match. Because here my units will be in watt and kilowatts, and they will cancel to give a percent. And here my units will be in kilojoules per kilogram, and they will cancel. So just as long as they're in agreement, that you'll get a value which will be fine and will make lots of sense. All right, so that is the efficiency of my cycle. So that answers everything related to this cycle. The last part of the question was, basically, I'm rejecting a lot of heat, right? This Q out is a non-negligible amount of heat. And it would be unfortunate just to send it into the atmosphere. I want to use it instead. So what I'm going to do is, this is my condenser. And what I'm doing, so this is 4 to 1, which is exactly what's happening here. This is from state 4 to state 1. So those values are known, right? My H4, my H1, those are all good. My mass flow rate, that's the mass flow rate of the water, all good. Everything is known. It's great. But what I'm saying is, I want to recoup that heat. I'll transfer it into some water, and then I'll pipe the water through my house and heat up the house, something like that. I want to use that heat for something useful. So what I'm going to do is I'm going to flow water from opposite the direction of the flow of the water through the condenser from 15 degrees C, and I want to cool it to 35 degrees C. I don't know, maybe I'm heating my jacuzzi, I don't know, hot tub. So what I'm going to do is I'm going to look at what happens in my condenser. We talked about it last week. Where's my equations? Here we go. And if you remember what I said last week, if we look at it, we know that there's steady state, so dE over dt is equal to 0. There is no value, there is no Q, and I know this is often confusing. There is obviously a Q, right? But it's because of what I'm considering as a system. There's a heat exchange between the fluids, but my system is limited to this. Here, there's no heat exchange with the environment, okay? So that's why my Q is equal to 0. Minus my work equal to 0, I'm not pushing or stirring or anything like that. Plus my flows, that's the important thing. So my sum of flows in minus my sum of flows out, exits. So this is the important bit. So what I'm going to say is my flows in, I have m dot, which is what I used before for the my cycle fluid. So I have m dot H4 going in. And then what else do I have going in? I have this point here. I labeled them 5 and 6 because I needed numbers. So, and this is the m dot, I'm calling it CW, cooling water. So in, I also have m dot CW for my cooling water, and I have my enthalpy at state 5. Minus my outs, so minus m dot H1, that's leaving here, and then minus again m dot of my cooling water, H6, which is leaving here. So those are all of the values that I know. And if I rearrange this, basically I'm going to get m dot H4 minus H1 plus m dot CW H5 minus H6. What I'm searching for is this. This is my unknown, right? I want to know how much cooling water I need to flow through in order to recoup this temperature range. So I'm just going to rearrange my equation here to give me m dot of my cooling water, m dot of my refrigerant, not my refrigerant, sorry, my cycle fluid. And then it's going to be H4 minus H1 divided by H6 minus H5. Note the signs again, because I would have had to bring MCW to the other side, so it would have been negative H5 minus H6. And to get rid of the negative, I just flip the signs. All right, so where am I going to get H5 and 6, you ask? It is water. So I can get them from the table. So I know that H5 is equal to HF at 15 degrees C, which gives me 62.9 kilojoules per kilogram. I know that H6 is going to be HF at 35 degrees C, which gives me 146.68 kilojoules per kilogram. Now all I got to do is I have to do this multiplication. And I know that I have 104.35 kilograms per second. And then I have my enthalpy values. And this gives me a value of 2,023.5 kilograms per second. And I can convert into kilograms per hour by multiplying by 3,600, which will give me 7.25 times 10 to the 6 kilograms per hour.